Hi, if we are studying the project J, for example, on a dedicated processor to generate a pulse frame, a stream of bits and then a kind of a time delay and the like. If we are here studying this, we have to think about the start button. How the start button, a physical device, a mechanical device, which is basically two contacts with then a spring that and something very simple like this is going to be connected to a digital system that may work, you see, as indicated here in the crystal, around 50 megahertz. So how can you connect that device, a key that is going to be interfaced by humans, to something like that fast? Okay, how can you do that thing? In this way, if we think about the push button, we may think about a device like this, a kind of a debouncing filter, because the phenomena that you see clearly in an oscilloscope when clicking a key is such the one that you see here in the picture, right? For example, when you click, you generate this kind of noise, and then while you are clicking, the signal gets a 0, and then when you are releasing, the signal goes back to a high level, something like this, you see? So you have a kind of a noisy signal that is not right for a digital system. This is why it is better to have here some kind of adapter. So you can get rid of the high frequency signals associated to the clicking and releasing of the button. Okay, so what you want here is, accepting some kind of delay. What you like is a very clear signal that is perfectly well a digital pulse, something that can, start or stop or whatever it is the function associated to the key, right? So this is what you like to get. Okay, so if we think about a button, it is basically a resistor or an electrical circuit that connects, the power supply, the VCC power supply, the battery to the ground, right? So here you are a 0 and here you are a 1. So when you click, you see the signal is normally high, and when you click, you generate this kind of bouncing signal, and then you get what you want, which is a 0. So when you release, this time here is when you release the button, something similar happened, because this device has associated a mechanical spring that allows it to go back to the initial position. Okay, it may be normally open and normally closed. Here you've got the representation of a normally open device. So when you click, you have an electrical contact here associating the voltage here in this wire, in this node, to 0, right? So this is what is an interface to a key. So this phenomena is in the range of milliseconds, okay? But you know that the digital circuit may be very well work in the range of nanoseconds. And that is why you've got that kind of difference in time scale. One thing is 1 millisecond, for example, and another thing is, 1 million nanoseconds, because, a digital circuit very well can work at 5.5 nanoseconds. So for a digital circuit, this phenomena here is just an eternity. It is a long time in the time scale of a digital circuit. Remember that the gate, for example, the propagation delay associated to or maybe very well that kind of 5.5 nanoseconds. So as you can imagine, the gate, if you connect the gate here like this, this gate is going to be sensitive to every signal bouncing that you have here. So probably the output signal is going to be ones and zeros, but it's going to be messy, very messy, not clearly digital pulse, right? So if you talk about sampling this signal, you know, if this is what you have in mind, sampling this signal, okay, sampling the push button, for example, active low, what comes into your mind is basically a data flip-flop, something that can be seen very easy as a device that is going to copy the input to the output when there is a rising edge from the clock, right? That is the process of sampling. The value, you know, it is going to work like this. The Q in the future is going to be a photocopy of the D. If D is 0, the value is going to be copied. If D is 1, this 1 is going to be copied the same way. But this only when you've got the rising edge from the clock. This is basically a data flip-flop. So what you are expecting here is that when you click and release the button, you like to have this perfect digital signal. This is the purpose of a sampler, right? But if you think about this, you see, if you are thinking about this, you have to choose the right clock frequency. This is what you like. Which is the right clock frequency? Which one? Okay, so this is why you can start investigating what may happen to a digital circuit like this when there is a high frequency clock, right? If the phenomena is in the range of milliseconds, as we have said, imagine that now you have a clock period around microseconds. So what is the meaning? That you have many sampling times because you have plenty of rising edges. So what is going to happen here is that you will generate a digital signal that is right, but you see the digital signal is going to bounce the same, whatever, several times and randomly. The same when you release the button. So this is okay, but you can imagine that this is not what you want. It is far away from what you want. So as you can see, if the frequency is too high, the signal is not correctly filtered. That is what happens here. Okay. Besides, what you get here is basically a random signal because the many bounces that you have here are dependable on the user, the pressure, and the materials, etc., related to the key, right? That is logically the case. Okay, if you have a key like that, the bouncings and everything is going to be sensitive to the many things that how fast you are pressing, what kind of materials, the quality of the device, and etc. Right? So that is the point. So if you follow the same discussion for the same chip, right? Okay. The data flip-flop for sampling the push button, trying to get the perfect pulse, which means a detection of the clicking. This is what you like to go detecting here. You may think about a clock frequency that perhaps is too low. What is the meaning of this? The meaning of this is that you have now very few sampling times. For example, here you are detecting a 1, and then later on you have another sampling time here, so you are detecting a 0, and later on you see you have another sampling time detecting a 1. In this case, for example, and accordingly to the process, the push button activity, you see, in this case, when the period of the clock signal is a lot greater than the milliseconds range in which is the phenomena established, you see, what you may like to get here, what is going to happen is that you're going to have a long delay. You see, here is when the thing happens, the click, but it is going to be detected perhaps a lot later. But, in some way, the output of the data flip-flop is going to be what you want. You see, the Q, in this case, is high, and then goes low, and finally goes back to high when you release the button. So that is a perfect pulse, right? But you know, it may happen in these circumstances that perhaps what you've got is a shorter click, okay? A shorter click, because that depends on you can click longer or shorter. So imagine that now what you've got is a shorter click, you see? You click and release faster. So what is going to happen now? Well, you are sampling a 1 as before, and then you are sampling a 1, and finally you are sampling another 1. So you see what has happened now is the signal is not detected at all. So the Q, you see the Q is kept high all the time, as if this fast click has not been existing. Okay, that's a problem. So this is because this happens is not detection happens because you have not enough samples per second. That is the point. So we can try to find something in between. A range of frequencies adequate to the physical phenomena around the clicking of a button. And this may look like something like this picture that you see in the tutorial about the debouncing filter, okay? Here you have rising edges, and you have sample values, and now you see some of them may be values in the forbidden zone. They are not clearly a 1 or not clearly a 0. So that is a complication because they may be very well undefined. But in the end, you see, at this frequency, you see, with this period, what may happen here is that the Q of the system, is going to be like this, for example, a perfect pulse. That means that the clicking has been detected. Or, if you like, you can generate another kind of output, okay? Another kind of output. Because, for example, you may like to know all the time that the key has been kept clicked. That's the point. So you see, the signal QB goes high when you click and then goes down when you release. That's another, it's a different signal, but it's the same thing. Both of them are digital pulses, perfectly well filtered, okay? And here, this cannot be solved, as you see. Something like this cannot be solved using a single data flip-flop. That is not the point. That is impossible. You have to add here some kind of algorithm. For example, what is said in this tutorial is that you go sampling, so the QA and the QB are kept low, so there is nothing here to do. But, for example, when 3 zeros in a row, 3 consecutive zeros are detected, now you've got the pulse. This is because now clearly the signal is stable, right? And then, for example, the same algorithm applies detecting 2 ones, right? If you are going to detect 2 ones in a row, this means that the signal is already high. In this way, you have it all. You have, not that much delay, an acceptable delay from the time when the user clicks the button, and you have a perfect pulse. But in order to do that, you need not a very simple data flip-flop, but something else, like a finite state machine, right? That's the point. That is what is proposed in the tutorial that you've got here in this application, right? Like here, right? So the debouncing filter is specifically this thing, okay? A kind of digital system that it's like a D flip-flop, but with something else. So that you can go and generate the perfect pulse that you like, whatever it is, a single clock pulse or whatever it is for the full duration of the event, because in some applications you would like to have one of them and some other applications another one. So that's the typical debouncing filter, a digital debouncing filter, specifically a finite state machine, right?